first want to thank my co-author Mark Willis and Rob Stewart. And so my topic is 3 VSP algorithms, surface seismic transform, NMO, and migration velocity analysis. I know it's a long title, so while I was doing this, I was thinking maybe I cannot give a best presentation since we have so many great students here, but at least I can win the longest title. Okay, so my talk outline, so why we're doing these algorithms. So because VSP has a higher resolution and also is target oriented, and it also have small data volume. We want to process on VSP and also improve the imaging for VSP. And this 3 algorithm is a pretty summary of what I did for the last 3 years of my PhD study. I choose these 3 representative algorithms, I code it. And so future work, we will apply those algorithms on has VSP survey and try to also extend these algorithms. So first algorithm is transforming VSP to surface seismic record. So when I first see VSP data, because we are familiar with surface seismic records, we want to see how we can use for VSP and whether we can apply surface seismic tools on VSP. So in Schuster's book 2009, he described several methods to transforming VSP to surface seismic records. And so I choose one basically for one easy to understand is using VSP primary convolved with the VSP direct wave. We can easily get those longer wavelengths of surface seismic primary. And this is what Schuster gives for the equation. And to investigate this equation, I extend this equation to several different parts because VSP has downgoing direct first arrivals and also outgoing reflections and also downgoing multiples. We separate them because when we process VSP, we can easily separate the outgoing wave and downgoing wave. That's a big benefit what we can do from VSP. And also, if we want to simulation shot, this is a simulation shot B for one side of the wells, and we separate it into 2 parts for the outgoing reflections with the direct first arrivals, and also from this side is direct arrivals convolved with the outgoing reflections. That can give you the 2 different illumination sides. And that's what we did for this part 1 and the part 2. And for the direct wave, when you want to transfer to surface seismic record, if you have very upper receiver, you can simulate that. But if you don't have, it's really hard to simulate first breaks. And also the receiver coverage in the borehole also give this limitation works. We described this in detail in this year's FCG abstract. Just submit today, and hopefully I can give a presentation in more detail in this year's SEG. So using this 2 simple 2 layers model, we have a simulation results. So this is what we did for surface seismic shots here using 2D acoustic finite difference modeling code, and then we simulated this surface shot from VSP the receivers in the borehole. We can see the simulation result looks really good, except those kind of artifacts, and also some aperture coverage. And so to limit this limitation artifacts, we try to use some taper to do this simulation, and those kind of taper to eliminate the edge effects can give a good measurements. We can see the artifacts is limited here. And also we try to see how this reduced receiver coverage can give you the limitation of this method, because for the field data, we cannot always have perfect borehole receiver coverage. So so if you just eliminate the reduce the receiver coverage, it will give you artifacts and also some kind of noise in there. And after that, we do a more complicated model about this one. It's a realistic model from Gulf of Mexico. We did a lot of work before this work done for this model. We do the modeling and also imaging, because it's really a complicated model and a lot of issues for the modeling part. And we also want to use this work to see our modeling to compare with surface seismic. And because this work is strictly applied for the 2D work, but we know our geo world is not perfectly 2D, it's 3D. So we try this algorithm on 3D model. So the left part is the actual surface shot we've made from the model, and then this picture is 2D, and this one is 3D. It's really hard to see something here from the light. We can see some 3D events from the 3D modeling part, and from the simulation, and we can easily, so there should be a blue light here, and because we separate it into two parts, one part will give you better illumination before that blue light candle the same outside of your simulation surface shots, because your ray pass, and the part 2 can give you a good approximation on the far outside receivers. And those 2D and those 2D and 3D simulation results gives our confidence to do this work. And using almost the same idea, we downward continue the surface shot to each level of the borehole receiver. We try to apply the normal move out velocity analysis too. But in contrast way, we didn't transfer the VSP back to the surface in the opposite way, because we want to get rid of the overburden part above the receivers. Since we can easily have some basic idea about the velocity information above the receivers from the logging tools or even from zero offset tomography analysis. So in this work, we assume if we know the basic information about this upper level velocity model, we downward continue all the surface shot to each level of the receivers. And another reason we did this is also because another company already patented about transfer all the receivers to the surface level. So in this way, we have like a simple 2 layers model to test this downward continuation, and this is the raw data we have, and using almost the same idea, Barry Hill style, we downward continue the surface shots to each level of the receivers, and then using this data, we apply the NMO corrections and the semblance structure analysis. So before the NMO correction, so this 2 layers simple model looks like this way to have the move out. And we just extended the equation about this move out equation, and using the velocity information above the receivers, we can make all the NMO correction to the bottom level of the receiver, and then do the spectral semblance spectral analysis to get the initial velocity model. And after we get the initial velocity model, we want to migrate it. And so we also did a migration velocity analysis. But for migration velocity analysis, it's really challenging since VSP is unsymmetric. So each period of migration ellipse is tilted in this way. So here, we try to we form a common image point form a common image point location, and try to have an efficient way to set up this intersection image points. And in this method, we need to transform from XOZ coordinates to the tilted ellipse coordinates, and then transfer back to XOZ coordinates to get this intersection points equation. I didn't show equation here, show in last year's SEG presentation. If you're interested in that, we can talk more detail in the, after this talk. And using of each intersection point is we can form a move out in the offset domain. It's conventionally, people use this residual move out analysis in offset domain, but here we separate it into two different steps. So first, you can use each of the intersection to form those curves, and each curve is indicate one receiver and all the offsets. And then each receiver will give you extreme point for each receiver, and to get using that extreme point, we can formula gather for different for all the receivers. So this is the unstacked common image gather for all the receivers, and then we just pull out all those extreme points to form the residual move out for one common image gather. So this axis is now changed to receiver depth. And we can see if we use correct velocity, the common image gather residual move out is really flat on the reflector. And if we use wrong velocity, it will curve. So for those method, we also construct VSP multi-layer models. So it's a 9-layer model, and this is modeling data we used. So I just used simply with only reflection events to simulate after the wave field separation. And this is an example of shot gather of VSP data. And here, using that model, we can first use a downward continuation with joint MO analysis to have the initial model. That's what we apply for the second method, and we can see it's really a good measurement for our model. And after we get this initial model, we can zoom into each layer and flat the residual move out. And we also try Kirchhoff migration image results is really coincidence with our tilted ellipse RMOs. So my summary is, VSP geometry is symmetric, so it is hard to apply velocity analysis tools from seismic data, surface seismic. And these three algorithms can be used separately or together to help VSP analysis. And transforming to surface seismic records from VSP data has some limitations, so we need to be very careful about that. And also, we have some, it's hard to see here, but we have some future work about the also deepening layers, and I also put a figure about the 3D, about our migration velocity analysis, but it's really hard to see from the light. And also in the future work, we will apply those algorithms on has 3D VSP data, and hopefully we can have some good results and also extended these methods. Okay, so my acknowledgement first is thank you for AGL and its supporters, and also really thank you for Halliburton. This is really like a joint project from Halliburton and Dr. Mark helping me a lot on this project. And thank you kindly for Michelle Simon and the colleagues at HAS for contributing the 3D time-lapse bucking data for our future research. We also express our appreciation for Richard Wendock and Sigma 3 for data preparation. Thank you.